So I need to remember what we did.
Sorry, Stefan, can I ask a stupid question? What is a Seedcorn?
Oh, sorry, Seedcorn. So we have a fund within the network. People can apply to this. You can apply for a small project up to 5K, £5,000. Where the basic rule is you've got to have somebody who knows about MDE and somebody who thinks they might benefit from doing something MDE, but doesn't have an MDE background. And because we're UK funded, you've got to actually have somebody in the UK that we can give the money to. And then you've got to have an idea of what you're trying to do with the goal of essentially exploring whether that's going to go anywhere, right? So you might build a little prototype, you might try something out. It depends on precisely what your idea is. In many ways, as long as you can convince us that you've got a plan and you're going to use the money sensibly over that time, that's kind of what we care about at that point, because we don't necessarily care about what precisely comes out of that specific project, whether you write a paper or whether you've got something you can sell at the end, because it's too short for that. But we care about that it allows you to explore the feasibility of that next step, and that hopefully it'll lead to something where you go, now we're going to do a bigger project together, and whether that's a PhD student spending some time at an industry partner afterwards, or whether that's actually bidding for a KTP project, or whether that's putting in a research grant together, or whatever it is. It's that the Seedcorn Fund project is there to give you that initial leg up to go from an idea that you discuss in the coffee break at the annual symposium to something that you go, no, actually, we have a really good understanding of what the problem is and where MDE might help, and we can put that down in a form that has a chance of getting some more reasonable funding to actually do some proper work. That's sort of the idea. Thank you for asking that, so that can explain that. Yes, so we had one of those with Stephen Niederer, who is professor in biomedical engineering here at King's. He looks at sort of models of hearts. And we were looking at whether DSLs and MDE can provide sort of a more intelligent, more usable interface for these sort of heart models. So computational models of hearts are important because people want to go to this sort of more personalized medicine. They want to sort of be able to say, Adekunle needs different treatment from Tom, even though, but maybe, and I know you don't, but even though they both maybe have a heart problem, their heart problems might be subtly different, and therefore different treatment is appropriate. Well, we can't do that unless we've got a model of each of their individual hearts, and we can plot that model and work out what treatment might have what effect. And so that's where those models are important. Typically, they're derived from imaging data. I'll have a picture in a moment that sort of tries and shows that a little bit. And then they do sort of simulation on top of that. And primarily, the kind of simulation they do is they look at how electrical stimuli sort of spread over the surface of the tissue. And they can put in place things like scarring and things like that and see how that affects it. And from that, they can sort of get a sense for how well the heart works or doesn't work and what might help it and so on. It's fairly complicated just because it's a huge amount of data, and it's three-dimensional, and it's got electrical properties for the various bits of tissue and things like that. So it's just getting your head around it is complicated. And it requires a range of skills because it goes all the way from image analysis all the way to simulation, HPC, because there's a lot of compute power that goes into this, and so on. So roughly, this is sort of what this looks like. You do sort of, that doesn't help on this screen, obviously. You do a CT scan of the heart, then that gets sort of segmented and image processed in various ways to try and essentially recover a three-dimensional model of the heart that then is sort of separated out into different functional parts and functional subtissues. And please do not ask me about what any of these are, because I will get it wrong. This image is blatantly stolen from one of Stephen's papers. They know what they're doing, I don't. But the main point is you now have these kind of three-dimensional things which are represented as big files with mesh data, so that's sort of triangular meshes. And what you do is these sort of colors, etc., they correspond to different types of tissue. And so in your simulation model, one of the things you want to do is you want to configure the simulation to say, what are the electrical properties of these different types of tissue? Which really is saying, every vertex in my mesh, what's the electrical property of that? And then you want to say things like, oh, no, actually, there's a scar here that has a different electrical property. So a subset of that mesh, you want to change the property. And then you want to say, and now I'm going to put an electrical stimulus there. And I want to see what happens. Okay. So you need to configure these simulations. And what they're doing literally is they've got the mesh files as a separate file. And then they've run the simulator on the command line. And it's got a command line that doesn't end. Because all the configuration information goes in there. But they did go and write a Python program that constructs the command line. But that's still essentially that, you've got, so it was the first time I saw arrays in command line parameters. So they literally have a dash, such and such, angular bracket 4, and you look at this and you go, I don't understand how you don't always get this wrong. Basically. They surprisingly, most of the time they make it work. But obviously, when they get it wrong, it's really difficult to spot the error until you throw it onto your cluster and let it run. And it comes back after 30 minutes going, I broke at step 0. My typical mistake is you put all your tissue in there, you say, this is where the electrical stimulus is, it runs, and nothing happens. And you look at it again, and you go, oh, my heart is here, my electrical stimulus is over here. It's not going to, nothing's going to happen. Or another typical error is when they define scar tissue, etc., they basically overlay a bit of mesh with different properties. So you redefine the properties of certain errors in the mesh, and that overrides those. And the way it works is the last one wins, basically. And that's usually what you want, because you want to define specific sub-properties of a submesh. But these different areas, they might come from different files. And if there's an overlap in those meshes, then you also have the last one wins, which probably isn't what you want. Right? And so you get all these kinds of things. And so what we did is, and I'm not actually showing an example of that, but we basically built a prototype language using TextX, because they really didn't want to even look at Eclipse or things like that. So TextX is a Python-based textual DSML approach, which allows you to define these meshes. So you don't actually have to write down the meshes. You basically just go, that file over there is where the mesh is, but then combine them and then sort of classify and provide the properties of the different parts of the tissue in there. Define where the stimuli are, etc. Which, from that we then generate the invocation of the simulator and all the vast and annoying command line parameters, because we can't really touch the simulator, because that's sort of an off-the-shelf thing. And then we kind of ran out of money a little bit at that point. So what I wanted to do more is to go, look, now we've got this language, now we can do all the beautiful error marking, etc. I did a little bit of that, demonstrate a little bit of the feasibility there, but we didn't quite have the time at that point to do more of that. But we were able to show, now you have this, now you actually have the potential to spot errors and highlight them and see that. And there is money in this, right? Because it costs money to run the simulation on the high performance computing platform. And if all that does is tell you your stimulus wasn't even on the heart, that's $50 that went down the drain, right? Yeah. If it can tell you that already when you've created the model, that's much better. Right? So it's for these kind of things. It's nice. We got funding to get the PhD student. We didn't quite manage to get the actual student, frustratingly enough, but we now have funding for a whole CBT, a whole Centre for Doctoral Training on digital twins for health. So if you have people who are looking for PhDs in this sort of area to do a PhD, we are just about to open the website and open call for applicants. So look out for that. First students to go through the door in 23, 24. I've
Nice.
not looked at the time, so I'm hoping I'm still in time. Are there questions?